In this video, we're going to talk about constructing models to solve problems. And so, of course, a lot of times people always ask, when am I going to use this? And so mathematicians and teachers come up with all of these word problems that are sort of non-realistic. However, they do require you to use a lot of critical thinking skills in order to help you solve the problems. And so we're going to look at some word problems that we can try to solve using some of the math that we've already learned so far. And so one of the things that you always want to do is you want to kind of follow a process. Now, this process may not work for every single problem that you encounter, but I will give some steps, as you can see on the screen here, that you can use in order to help you solve word problems or construct models to solve problems. Of course, you want to read the problem for understanding, right? Sometimes you have to read a problem more than one time to get a full understanding of the problem. The second thing you can do is you can draw a diagram if it's possible to do so. As the old saying goes, a picture is worth 1,000 words. And so sometimes when you see things graphically or with a picture visually, you can kind of reason a little bit better. So that may be helpful. In all of the problems that we're going to do, we're going to choose and define a variable, state what your variable is and what it means. You know, what is X if you're going to use X as your variable? What is K if you're going to use K as your variable, or what have you? And what you want to do ultimately in constructing a model is to basically write an equation that relates the variable that you have with the context and the concepts of the problem that you're trying to solve. Usually you're going to solve the equation, and then you can check and present your solution to make sure that it makes sense. For instance, if we're talking about geometric figures, you solve your equation and you get a negative answer, you know for a fact that that's not going to be a proper solution. So use information like that to kind of help you determine if your work was on the right track. Here we have a bunch of topics with formulas that go along with them. A lot of these formulas you already know. For instance, the formula for the perimeter of a rectangle is twice the length plus twice the width. The area of a rectangle is how much space is taken up. It's two-dimensional. So it's the area equals, not multiplication there. So there is an error in my notes. I'll make sure I correct it when I post your notes. But area equals length times width. The area of a circle is pi r squared. The area of a triangle, 1/2 the base times the height. Uniform motion, that is something that comes up quite often in the sciences. Uniform means we're assuming that whatever object is traveling, we're assuming that it's traveling at the same speed across a certain time period. So there's no speeding up or slowing down. We're assuming that it's on average going the same speed. And then we have percentages. I just wrote this formula here to remind you of how to take a percentage. You multiply the decimal representation of a percentage, which I have as percent here, times what number you want to take the percentage of, which I give B here. So I have amount equals the percent times the base. Some people call the number that you're taking the percentage of the base. That'll give you the percentage. And this comes up when you pay premiums, when you pay taxes, or if you want to take a percentage of a certain amount. This is what you do to calculate the percentages. Now, there are a wealth of application problems that we can look at. I'm just going to look at a few examples to get your head rolling around, setting up and solving word problems. Let's jump into the first example here. It says Jeannie Thong bought a Ford Mustang GT for a total cost of $18,966, including sales tax. If the sales tax rate is 9%, then what amount of tax did she pay? And so if we solve this problem here, remember when you go to the grocery store, if you have to pay sales tax on groceries, or if you go to like Walmart or Target or whatever, you remember you always, to calculate your total amount, you get your selling price, you add the amount of tax that you have to pay, and that's going to be the total cost at the bottom of your receipt that you actually have to pay, right? And so what we have here is that we know that the person paid a total cost of $18,966. We know that they did 9% taxes, but we want to know the amount of taxes. Well, we don't even know the selling price, and the tax amount is based off the selling price. So what we're going to do is we're going to and I'm going to see if you can actually see this here. I'm going to let X represent the selling price. So instead of writing the word I'm going to replace that word selling price with X. And I know that my tax amount is going to be 9%. To take 9% of something, we multiply 0.09 times that selling price, and that's the amount of taxes. And so now I have an equation that relates all of those variables. X plus 0.09x, well, that's a 1 in front of the x, and 1 plus 0.09 is 1.09. So I get 1.09x equals 18,966. I divide both sides by 1.09. And what I have here is that X, which is my selling price, I'm going to get my calculator. So I know that I said that in our class we don't use calculators. But actually in this section, I don't mind you picking up a calculator to do a calculation like this. We get X equals 17,400. And so that is our selling price. Now, we want to know the amount of taxes she paid, right? No, now we know the selling price. Well, the amount of taxes she paid is 0.09 times the selling price, right? So if I did 0.09 times that 17,400, we're going to get that the amount of tax .09 times 1,77400 is $1,566. It's $1,566. And that answers the problem, all right? What you could have also done was you could have subtracted these two values here, the 17,400, which is your selling price, from your total cost. That would have also given you your amount of taxes as well, which would be $1,566. All right, let's look at another example. Julia's soybean field is 3 meters longer than it is wide. To increase her production, she plans to increase both the length and width by 2 meters. If the new field is 46 meters squared, or square meters, larger than the old field, then what are the dimensions of the old field? All right, so this is one of those problems where a geometric representation or a picture or a diagram will be helpful. So we have one field sheet. So we have an old field that is rectangular because it has a width and a length. And then we have a new field, which is also rectangular. All right, so I'm going to draw a rectangle for my old field. Let's say it looks like this. And so she said that the field is 3 meters longer than it is wide. I'm going to let X represent the width of the old field, right? If it is 3 meters longer than it is wide, and I know that it's X meters wide, then the length is X plus 3 meters, all right? That is the old field. In order to increase production, she plans to increase both the length and width by 2. Well, if my width is X, then my new width is going to be X plus 2. And if my original length is X plus 3, and I add 2 to that, I'm going to get X plus 5 as my new length. So this is the picture here. And I chose my variable W, normally I'll use W, but I use X here because it gives me my length as if I already know my width. It says 3 meters longer than it is wide. Well, I don't even know how wide it is. That was a clue that I'm going to use my variable to represent the width. Now it says if the new field is 46 meters squared larger than the old field. This has to do with area. One way that I know that is because this unit here is squared. And so that represents a two-dimensional figure, which is area. And then it doesn't have to do with like how long or how the fencing around the field or anything like that, all right? But the new field is 46 meters squared larger than the old field, right? So remember, the area of a rectangle is length times width. And so if I multiply the X by the X plus 3, this is the area of that rectangle, and the area of this field or this rectangle is going to be X plus 2 times X plus 5. And so it's saying the area of the new field, so this one right here is 46 meters larger than the old field. Well, if my old field is X times X plus 3, all I have to do is add 46 to that, and it's going to be exactly the same as the area of my new field. So now I have an equation set up. Let's solve our equation, right? I use my distributive property. I want to solve for x. I get x squared plus 3x plus 46. And when I use my FOIL or my repeated distributive property, I get x squared plus 7x plus 10, right? This is quadratic, right? But look here, both sides has an x squared. So if I subtract x squared from both sides, although this equation looked quadratic, it actually is linear, right? Because those cancel and I get a 3x plus 46 equals a 7x plus 10. I'm going to subtract 3x from both sides. I'm going to subtract 10 from both sides. And then I'm going to divide both sides by 4. And I'm going to get x equals 9, right? Now, x equals 9. 9 was the width of my old field, so that's 9 units. And since this length is not 9 plus 3 or x plus 3, then my length is 12 meters. So the dimensions of my old field is 9 meters times 12 meters, right? Now, I'm going to check myself to make sure that this makes sense, right? I know that the area of my old field is 46 meters squared larger than my old field. So the new field is 46 square meters larger, right? Well, the area of my old field is 9 times 12, which is 108. The area of my new field, well, I added 2, right? So 9 plus 2 is 11. So the width is 11. 9 plus 5 is 14. And I don't know 11 times 14 in my head. So that's 11 by 14, which is 154. And if I do 154 minus 108, that's actually 46, right? These are meters squared, right? Which is what I expect in the problem. And I know you can't see much of that there. So I'm going to show you what I did. Again, what I did there is I did a 9 times 12, which is 108 for the old area. The new area is 11 times 14, which is 144. And then I subtracted the 2 because it said that the area of the new field is 46 square meters larger than the area of the old field. All right, so that is that example. Let's look at our next example here. During a blizzard, Lisa averaged 23 miles per hour on a trip from Dawson City to Envic on the Dempster Highway. On the return trip, she averaged 20 miles per hour, and the trip took 3 hours longer, right? So she's going to the city from Dawson to Envic, so from point A to point B, and then she comes back from point B and goes back to point A. But she's going a different speed or rate, and then it's taking her a little longer since she's traveling slowly during the blizzard. And our goal is to find how far it is to go from point A to point B. All right, I guess I can draw a picture to represent this scenario here. All right, I know that they use Dawson City and Envic. I'm going to use point A to point B. All right, I have point A here, point B, right? And so I know that when she is on the way from point A to point B, her rate is 23 miles per hour. I don't know her D, and I don't know how long it takes her, right? On the way back, she's going 20 miles per hour. I don't know the distance. That's what we want to find. And I don't know the time, but they do give me a little information about the time, right? With the time, it took 3 hours longer than it did on the way there, right? So it's giving me the time as if I know already how long it took her to get there. That's a sign that that's going to be a very important variable in your equation. And so I'm going to let my variable, I'm going to leave it as t, be my variable. And so then I can write the time that it takes her to go back to Dawson City as however much time it took me initially plus 3. All right. Now, because this has miles per hour and this is about traveling, I know that this was a uniform motion problem. And that's why I knew that I'm going to use D, R, and T, right? Because the formula for uniform motion, distance equals rate times time. Now, with this said, right, I want to know the distance from A to B, Dawson City to Envik. I know that I have my rate here. I know the time is given by the variable T, but I don't know the distance. Here I have a rate and a time representation here. And so what I'm going to do to set up my equation here is to realize that, okay, well, the distance it takes me to go from A to B is exactly the distance it takes me to go from B to A, right? And so although I have a distance equals rate times time for the way I go up, I'm going to represent that with a subscript 1. That is going to be a D1 equals 23 times T. Rate is 23 miles per hour. T is my time, which is my variable. And then I have a distance equals rate times time on the way back. I'm going to give that a subscript 2. And so D sub 2 is going to be how fast they're going on the way back, which is 20 miles per hour. And I multiply that by the time it takes, which is 3 hours more than it did initially. And so I get 20 times T plus 3. And with that, since I know the distances are the same, then I take these two expressions for our distance, set them equal to each other, and at least I can solve for the time. And once I know the time, I can put that time and replace it back into either one of these equations, and I will be able to come up with the actual distance. And so if I solve this equation for T, this is a linear equation. We need to isolate T. That means get it on one side by itself. I subtract 20 T from both sides, divide both sides by 3, and I get 20. That means now my distance, my rate was in miles per hour, my time is in hours, so this is hours, all right? And so that's T. That is not the answer to the question because it's asking me how far is it, right? And so I can go to either equation, D equals 23T, plug in 20 for T. I get 460 miles per hour times hours. The hours cancel, and so I get miles. Notice you could have went into the other equation. You got 20 times 20 plus 3, or 20 times 23, which is the same thing we have here, but in a different order. And you will see that you have 460 miles. All right. And so that is an example of using, looking at a uniform motion problem. They all don't work this way. Sometimes they'll give you a total time, or sometimes they'll give you things about rate, right? So read the problem and try to reason through it. The thing that helped me make my equation here is the fact that they were going the same distance in both directions, right? And so if they're going the same distance, the distance is going to be equal in each case. You're going to see on your homework where I give you some problems where you just solve some equations for a variable. These are literal equations, meaning they have variables that have real life meaning. For instance, this is an equation that we use to convert from Celsius degrees to degrees Fahrenheit, right? And so if we wanted to go in the opposite direction and convert Fahrenheit to Celsius, then what we could do is we can solve this equation for C instead and have it written in terms of F. If I were to do that, which is asking me to do here, I just solve like I normally would. We treat F as if it is a variable, which it is. And if I solve for C, I divide both sides by 9/5, which is the same thing as multiplying by the reciprocal. And so this gives me a formula for converting from degrees Fahrenheit to degrees Celsius. All right, that's just an example. You'll see some other examples that may be a little bit more complicated, may involve a little bit more manipulation, but I think this is all we're going to have for this video today. I'll see you next time.